All right, in this lecture, we're going to be looking at the calculus of parametric curves. And first, we'll kind of break this lecture into two parts. We'll do part one in this video, which will be focused on differentiation. And then part two, we'll look at integration. Okay, and so again, for this video, we'll look at differentiation, and then the next time we'll look at integration. And I want to start with an example. Let's consider a parametric curve given by x of t equals 2t plus 3 and y of t equals 3t minus 4. Okay, and let's look at this over the time interval -2 to 3. If we look at a sketch here of this parametric curve, last time we, in the first video, we learned how to get a sketch of these things, but I'll just go ahead and write one down for now. So we start here at when t is -2, we're at the point -1, -10. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Okay, so here's our point when t is -2. And then when t is 3, we are at the point, let's see, when t is 3, we should be out at 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Out at 9, and then up to 5. 3, 4, 5. Okay, so you have something like this. Again, this is just a sketch, but we see it's indeed a line. And we're looking at differentiation now. And so we could try to find the derivative of this line, right? And all the derivative tells you is the slope of the tangent line at a given point to a curve, right? And let's compute what the derivative would be by eliminating the parameter from these parametric equations. So we can find dy dx by eliminating the parameter, right? And so we had, let me copy, we had x equals 2t plus 3, y equals 3t minus 4. Well, let's say we solve x first. So we can solve for t from the x equation. So we'll get 2t equals x minus 3. So t equals x minus 3 over 2. If we plug that in to our equation for y, we get y equals 3 times t, which is now x minus 3 over 2 minus 4. The equation for y simplifies to 3/2 x, and it looks like it's going to be minus 9/2 minus 8/2, which is 3/2 x minus 17 over 2. So this is the equation for our line. And we can find the derivative right away now. Now that we have an equation for our line, we know that the derivative is just the slope, right, which is 3/2. So that's one way we can find the derivative of a parametric curve, is to simply eliminate the parameter, get it back to a function in Cartesian coordinates, and then take the standard power rule derivative, or whatever derivative rule you would use that we're used to. But what if we were to compute, let's consider x and y again as functions of t. if we were to just compute their derivatives outright, we would get x prime of t is 2 and y prime of t is 3, right? Because we're taking the derivative of 2t plus 3 with respect to t now, which is 2, and then the derivative of 3t minus 4, the derivative of that with respect to t is 3. And if we look at y prime of t over x prime of t, we get 3/2, which is the same as what we calculated from first converting back to rectangular coordinates. That is not a mistake that these are the same. This actually leads to a theorem. So, theorem. If, let's assume x of t and y of t are continuous and define a parametric curve. Let's also assume that x prime and y prime exist. And let's also further assume that x prime is not 0. Those are all necessary conditions. So then what is the theorem? So, well, then the derivative is given by dy dt over dx dt, which was, as we wrote on the last slide, y prime of t over x prime of t. So we can use this formula to our advantage to calculate the derivative without even having to go through the work of rewriting a parametric equation as a standard xy curve. So now that we've seen that indeed we have a way of calculating derivative while remaining in parametric form, let's see what else we can do while still being in parametric form. If you think back to Calc 1 and Calc 2, what did we do after we learned how to take the derivative? Well, then it's, let's find critical points. Let's find maxima and minima. Let's find slopes of tangent lines. Let's find equations for tangent lines, et cetera, et cetera. So we still want to be able to do all of that. So let's go through a few examples and see how we can find critical points or equations of tangent lines still, but now in working in parametric form. So let's do, whoops. Let's get back to where I want to be here. Let's do some examples. And the first one will be finding critical points, right? Which, again, if we can find critical points, then we can find maxima and minima using first derivative, second derivative tests, things like that. So let's say we have the following parametric curve. X of t equals 2t plus 1. Y of t equals t cubed minus 3t plus 4. And let's look at this over the interval -2, 5. Okay? And we want to find the critical points of this function, right? This represents some curve in the Cartesian plane. We don't know what it is in rectangular coordinates or anything, but we can still find critical points, even though we may not explicitly have the equation of the function at hand. So how do you find critical points? You take derivatives, and then you find the points at which the derivative is equal to 0. So we want to find points x and y where dy dx is equal to 0, right? Well, we can solve for dy dx now. What is dy dx? dy dx is, by the last theorem, y prime of t over x prime of t, which is then, in our case, let's calculate this. So y prime is going to be 3t squared minus 3 over x prime of t, which is 2, right? And to find critical points, we want to set the derivative equal to 0 and solve for t values. If we set this equal to 0, well, the 2 vanishes, so then we just get 3t squared minus 3 equals 0, which is the same as saying 3t squared equals 3, which is the same as saying that t squared equals 1. And if we have t squared equals 1, kind of going back up the page here, well, then we get that t is plus or minus 1, right? So these are the times, right? We have this curve explained in terms of the parameter t. So we have the times at which the derivative vanishes, but we don't know where those points are at. But all we need to do now is take these points and plug them back in to our parametric equations, because then we'll get the x and y coordinates at those specific times. So if we have, let me copy the parametric equations down for the sake of convenience here. It was 2t plus 1, t cubed minus 3t plus 4. The critical points, so we have critical points at t equals plus or minus 1. Well, let's just look at these. At t equals 1, we get that x is going to be 3, and y is going to be, so if we plug in 1, we'll get 1 minus 3 plus 4, which is 2, right? So that means we have a critical point at 3, 2. So we've solved for one critical point. Let's solve for the next critical point. Well, we know it's at time t equals -1, and now we just plug -1 into x and y here. So if we do this, we'll get x equals, it'll be -2 plus 1, so -1, and then y is going to be -1 plus 3 plus 4. And in this case, we would get 6 for our y value. So we have another critical point at -1, 6. And so we found the critical points or potential maxima and minima of this function without even explicitly knowing what the formula for the function is in the standard xy coordinate system. However, we do know its information in parametric form. We know what this curve, how this curve is expressed parametrically, and so we can do that. The next example I want to cover, here's the example. So this will be number 2. The next example, the first one was finding critical points. Now this one will be finding equations for tangent lines. Okay, so to find equations for tangent lines, let's look at a problem here. So this problem says find the equation of the tangent line to the curve defined by, so find tangent line to the following curve. X of t equals t squared minus 3. Y of t equals 2t minus 1 at, so let's find the tangent line to this curve at the point t equals 2. Okay, so I won't draw this out explicitly, but I'll give you kind of a sketch of what's going on here. So, you know, we have some curve like this. I roughly know it's going to take this shape because I see that it's quadratic in the x direction here. So there's going to be critical points along this line, right? But we're not interested in finding the critical points right now. What we want to do is somewhere in here, you know, maybe t equals 2 is here. We can say, here's t equals 2. There's a tangent line to this curve at t equals 2. Call this tangent line here. Right? And what the problem's asking is, what's the equation for this line? Okay, so this is kind of a sketch of what this problem's asking is, you know, we have some parametric curve here, and we're interested in the tangent line at a given point. In this case, this is our curve given by t squared minus 3 and 2t minus 1, and we're looking for the equation for the tangent line at the point t equals 2. So let's see if we can do that. And for a line, right, there's two ways you can express a line. There's slope-intercept form, and then there's point-slope form. So we can have either y equals mx plus b, or this is slope-intercept form, right? Slope-intercept. And then you can also have point-slope form, which is y minus y0 equals m times x minus x0. And so these are two equations that we can use to get a like somehow we're going to have to take information from this curve and this point. We need to get enough information to either be able to use point slope form or slope intercept form. So we'll keep that in the back of our head as we are trying to solve for this equation for a tangent line. There's kind of two equations here that we could possibly use to our advantage. In the first one, you need a slope and the y-intercept. And then the second one, you need the slope and a point, right? So we'll see which one we can use. First, in both cases, we need to find the slope, right? What is the slope of this tangent line? Right? That's exactly what the derivative does, is it tells you the slope of the tangent line at a given point. So the slope of the tangent line is going to be given by dy dx at t equals 2. This will be our slope. Okay, so this is how you find the slope of a tangent line, is you use the derivative, because that's what the derivative tells you. It tells you the slope of the tangent line. So let's solve for m here, right? So we've said m is going to be equal to dy dx at t equals 2. Well, what's dy dx? We learned that dy dx is y prime of t over x prime of t. Right? And so, again, we're going to take this and evaluate it at t equals 2. Right? Kind of off to the side. I'll remember like that's where we want to be here. And so our y of t was 2t minus 1, which means y prime of t is going to be 2. And then x of t was t squared minus 3. So here, maybe I'll write these down again. X was t squared minus 3, or is t squared minus 3, and y is 2t minus 1, right? So you can see y prime will be 2, and x prime will be 2t. And this gives us that the slope, in general, the derivative is 1 over t. But at t equals 2, m is 1/2. So that means the slope of this line, this tangent line up here, is 1/2. So we found m now. We have a slope. And now we need to either find a slope or we need to find the y-intercept, or we need to find a point. And I claim it's always easier to find a point. And we will want to use point-slope form. So here we found the slope by taking the derivative. And now, so slope m equals 1/2, which, again, to reiterate, was the derivative of our curve at t equals 2. Okay, and now how about the point? Well, we're at t equals 2. So when t equals 2, x equals, well, it's t squared minus 3. So 2 squared minus 3, which is 1. And y is 2 times t now, which is 2 minus 1. So y is 3. So now our point, so we have a slope of 1/2, and we have a point of 1, 3. We have now enough information to completely fill out the formula for, or point slope form of a line. And point slope form said y minus y0 equals m times x minus x0. Okay, and plugging in, right, so this is what's going to be our point x0, y0. Right, and m is 1/2, so we'll get y minus 3 equals 1/2 times x minus 1. And you can leave it like this. Sometimes it's a little nicer to, and a little more aesthetically pleasing to express it than as slope-intercept form. So if we do that, we'll get, let's see, y equals 1/2 x, and then it's going to be minus 1/2 plus 6/2, right? Because we added the 3 over. So this means we have an equation for the tangent line given by 1/2 x plus 5/2. And this is our equation for the tangent line to the curve at the point t equals 2. So those are the two pretty common and useful examples. We'll hopefully in recitation and in the homework, we'll go over more examples like this. So that's that concludes what I wanted to say about the first derivative of parametric equations. And I want to make one quick remark. And the remark is that we can define second derivatives and higher order derivatives of parametric curves. So we can define second order derivatives. Right? What's the first order derivative? Well, the first order derivative, here's first order, was dy dx. So what is the second order derivative? Well, it's the second derivative. So that means you take the derivative of the derivative, right? And then we want to see what this is. And we denote this, it's kind of his notation here. This is d squared y dx squared. this is what we call the second derivative, right? And in Leibniz notation, we use d squared y over dx squared. Well, so again, that's the derivative of the derivative. But what is the derivative? We're looking at the derivative in parametric equations. So this is y prime of t over x prime of t, which may be a little nicer or a little more clear to write as d dx of dy dt over dx dt. There's some simplification between these two steps, but ultimately what you end up with for as an equation for the second derivative is d dt of dy dx over dx dt. And if you'd like a nice little exercise in playing around with derivatives and having to use like chain rule and stuff like that, I would challenge you to try to get from this step to this step here, to where we get our actual, the formula we use for the second derivative defined in terms of parametric equations. All right, so that wraps up what I wanted to talk about for differentiation of parametric curves. And then in the next one, we'll talk about integration of parametric curves. And then from there, we'll move on to polar coordinates. So I will talk to you guys then.